Okay, so graph theory. Looking at that term, what comes to your mind? Like,
Graph.
okay, well, what is a graph, right?
Graph is like what x and y coordinate.
Okay,
Infographs.
those are one type of graph.
Histograms.
Infographics, right?
Oh,
It's like a lot of times you see information presented as graphs,
line
right?
graphs.
Line graphs, yeah, those are all graphs. Bar charts, pie charts, and all those things are called graphs, right? But in computer science, let me see what's in the chat window.
You can make things with graphs.
Yep, you certainly can. Okay, in the context of computer science, this type of graph is, what we're referring to.
Undirected graphs and complete graphs.
Yeah, so a graph, right, is a collection of vertices. Like in this one, the upper right corner, it says A, B, C, D, right? In the circles. Those are called vertices, right? Vertex, vertices, or nodes, or node, right? So each one of them is a node. And then the lines between them are called edges, right? The edges connect the nodes. Okay, so these kind of graphs are the specific, what we're referring to in the computer science context. When we say graph, that's it. That's what we're talking about. Okay, so in the elementary level, all the graphs we talk about are going to be undirected graphs.
There are no arrows on the edges.
Right, there are no arrows on the edges, so there's no direction, right? You can go either way, that means, right? You can go from A to B, B to A.
So like, is it just normal and like those normal shapes? They just
Yeah.
have vertices.
I can, what I can show you is, in the junior level, right? There's also graph theory, right? They also talk about the exact same content as you guys do, all these here.
It's like more advanced though.
It's not necessarily, yeah, it is more advanced, but it's more mathematical, I guess. And so in there you have these, we talk about these directed graphs. But in our context, right, in the elementary division, right now, we're going to talk about these undirected graphs. So that means when you have this one in the upper right corner, you got A, B, C, D, 4 nodes, and you got those lines connecting them, right? You can, when we say walk on the map, right, or walk on the graph, or traverse the graph, when we talk about that later, we can go from A to B and also B to A, right? There's no direction in that connection, in that edge, on that edge. So, and another term is a complete graph. A complete graph means all the nodes are completely interconnected with each other. What does that mean, right? Basically, if you look at this, that's a complete graph, right? This,
Every
what do you call that?
vertex
That's
to each-
ones with 5 nodes, right? A, B, C, D, E.
Mm.
So A is connected to each and every other node, right? B, C, D, E, with a direct line to it. That's called a graph. I mean, a complete graph. Right? With a complete graph, you have this formula here. The number of edges equals to the number of nodes plus the number of diagonals.
What does it mean by diagonal?
Right.
like-
The diagonal connections.
oh, okay.
Wait, so does
One,
that mean
two,
there are like only one straight line?
In which one?
A, B, C, D, E.
A, B, C, D, E.
Everything except that straight line. I mean, that two straight lines.
What do you mean two straight lines?
There's
C,
five
D,
diagonals.
C, D, and the one in the star.
Wait, the four? Or-
1, 2, 3, 4, 5, right? There are 5 diagonals. And well, it's basically
Okay,
Um,
yeah, that's five. No, I think that's.
you have 5 nodes here, right?
Uh-huh.
5 nodes here. And you have 5 diagonals here, and then you have all together 10 edges.
So.
That's basically
the-
That's basically what this is saying. It's not really that complicated. If you just add them all together, you pretty much even get to that, right? And if you look at this, right, this is a 4-node, A, B, C, D, 4 nodes, right? And if you make it a complete graph, you just need to add this one connection, right, C to D. And you can see that you got what, 1, 2, 3, 4, 5, 6
Picture?
edges, right? And then you got 4 nodes, right? 4 vertices plus 2 diagonals, right? 6. So it's just that, you know, with all the complete graphs, that is always true. So like if you have like a 3 node graph, what do you get? Right? You don't have any diagonals, right? Actually.
Yeah. It's just.
So you got 3 nodes, 3 edges. That's it. Yeah, that's simply, I mean, that's the simple definition of graphs that we're talking about. Okay, graphs, and then complete graphs are so defined. And now, what we call a path is basically a way for you to go from one node to another. Right. It could be to any other. And then you're going to go walk through a bunch of other nodes, right? A bunch of from 0 to multiple. And also you're going to go through a bunch of edges, right? That's basically, it's like a path in the woods, right? When you're going out taking a walk. You're going to go, by a couple of landmarks, and then you're going to go through like roads and stuff. Right? A connected graph is another term that says if you do have a path from one node to any other node in the graph, right? That means the graph is completely is connected. Everything is connected, right? But in this case, the one on the right hand side, right in the box, has A, B, C, D, 4 nodes, and then you only have connections from A to B and C to D, right? There's no way to for you to go in this graph from B to C, right, or from A to C. And there's just no path there. Obviously, this is so obvious, right? You can look at this and see exactly what that means. But when we talk about graph, what comes to my mind, actually, if I may go to Google and search for internet maps, right? So if I just go look for images.
Whoa.
Right. So there, those are real complicated graphs, right? But they're graphs, right? So in this kind of case, you can't just eyeball and say, are they all connected? You don't know, right? That's where, that's when, you know, all the theory and math and all these kind of stuff make sense, right? Because with these simple graphs, you obviously don't need all that theory, right? But this is basically just to demonstrate, right, what a connected graph looks like and what a disconnected graph looks like, right? So, and also with path, right, we have the concept of length of the path. So when you have a direct connection, right, from B to D, in this one, there's no direct connection from B to D, right? So there's no path from B to D of length 1, right? But there's one from C to D, right? And from B to D, the length is at least 2, right?
Okay.
But you also have another one that goes from B to A to C to D that has a length of 3, right? So,
per edge is 1.
yep, every edge is counted as 1. So that's what length means. Okay, in this graph, do we see how many length of length 2 from B to D? Can you from B to D, right? From B to D. Length 2. Length 3, sorry.
Where's length?
Wait. What did I say? See any other path length 2 from B to D? Oh, yeah. So in this one, it says BAD is a length, is a path. BAD is length 2, right? B to A and A to D. Right. BED is another one, right? And BCD is also another one, right? And length 3, for example, you can go from BCED, right? Or BCAD, right?
BAE. Wait, no.
Yeah.
Oh, yeah, BAE.
BAED, that's 3, right?
BAE.
And again, why are we talking about this? When we look at this, these graphs, right? These complicated networks, then we have to know how to get to somewhere fastest, right? Because that makes sense, because you don't want your traffic or your data, your package to be on the network going places. It takes time, right, to go from one node to another, you know, I mean, if you're making a phone call, for example, and the data coming out of your phone gets routed all the way to Europe and then come back to the US, that'll take a lot of time, right? Then the other person hears you. When they do hear you, they hear a very choppy voice, right? That's what happens when you know, traffic gets routed in the wrong way. Even though, you know, the internet, when it's initially designed, right, when it is built, the purpose is for it to be very resilient, meaning that let's say if you have this complicated network right here, that's not like a lot of computers on the internet talking to each other, and the traffic from one end from one node here, right, down south, all the way up to the north, can go through, many different routes, right, to get there. And you want to always try to, the first thing is guarantee that this data will get there, right? That's the initial purpose of the internet, resiliency. Meaning that if something happens in the middle, and somebody, chop the line, or somebody run a truck and run to an electric pole and something get broken. The internet will find another way to get your traffic over to the other side, right, to its destination. But then also, when the internet, more and more things gets onto the internet, you also want to make sure that, well, even today, we're not making sure of anything really. It's just that technology has improved so much, right? For the most part, we can, have a very good possibility, like 99% of the time, your traffic, or the speed of your data that travels from one point to another in this complicated graph can be guaranteed. Not guaranteed, but you know what I mean, right? You have a good chance of getting a very good speed, for that traffic to go through this network. Then anything can happen, right? Especially when for example, when you are talking to on a mobile phone, right? And think about this, right? Because if we look at this picture, this picture shows, intercontinental connections, right? But if you zoom in, right? If you zoom in here in the United States, and you're driving down a highway at the speed of 70 miles per hour, sorry. You're talking on a phone, and the phone is actually connected to a cell tower, right, by the side of the highway. And you could be connecting to one tower this second as your car drives along the highway. The next second, you could be connected to another tower, right? But this network needs to figure that out, right? As you are driving, as you're going along, and that next tower will be able to, handle your traffic, because it will need to pick up your voice from there, and then again route it to the correct destination, right? The other person that you're talking to. So this is basically the reason that we're talking about. We're just studying all these stuff, right? The graph theory. Yeah. Yeah. Thanks. Sorry. Yeah, I forgot to go over to the chat window. So that's that. And okay. So we have gone through the connected and disconnected graphs. Next is cycle, right? In this complete graph, you can see that there are lots of cycles in there. All right. So like the first one, A, B, D, back to A. That's a cycle. That's a circle. Or you can go A, B, C, D, E, A, right? That's another, cycle. And because when we're talking about undirected graphs, and these are actually the same cycles, right? The same edges are in there.
So it starts
When you
from
walk through
one
it.
point and then it goes over, and then after it goes back to the
Right.
point of start.
Right. So when you can do that in a graph, that means there are circles in the graph. Right. So cycles always have, 3 or more vertices. It's 3 or more nodes because 2. Actually, when we talk about directed graphs, that was also allowed. So, but here we don't treat that as a cycle, okay, in the undirected graph. So there's a famous problem called the traveling salesperson problem. What that problem asks you to find out is that on a map, right, a map where you have cities and then roads, right, between, or villages and roads between these places. And so the problem is to ask you for a
Cycle that contains
find a cycle that,
contains all-
for the, yeah, contains all the vertices, all the nodes, or in the salesperson's problem case, all the cities, right, all the towns that this person has to go to, sell stuff, and then eventually come back home, right, to his where he started, where she started. So that's like in this one, I guess the probably, I mean, you can again eyeball it, right? If you go from A to B to C to D to E and then back, that would be it, right? That would be the shortest way for the person to go, through all the nodes and without, traveling the same road twice anywhere, right? And also, visit all the nodes, visit all the towns. So that is one of the I guess most famous problems in graph theory. And another one is this called traversability. Okay,
Ever versions of
this is Königsberg,
Oh.
right? This is what is it? Prussia in the old days, right? It's German, really today, right? The city of Königsberg has, the city is sitting on both sides of a river. So you got A side, B side, right? On 2 sides of the river, and then you got 2 islands, C and D, in the river, in the middle of the river. And then you got all these bridges connecting the land, the mainlands to the islands. Right, and then also, anyway, you have these 7 bridges connecting them, right? So the problem is asking you to figure out if anywhere you start, right, in the city, can you walk through all the bridges once, right? But only once. So if you start from A, for example, you go through P, right, you can go through that, but you have to walk over the bridge, all of them, right? Once, but only once. You can't go from A to D here and then go back. That would be counted twice. So the question is asking you, can you do that? Right? And the condition is obviously that you can't jump into the river to, go to the island, for example, and you cannot
The starting and ending points of the walk need not be the same. So
right, but it is actually, well, yeah, it means that you don't have to, yeah, I guess that's pretty much it. Right, so that's a famous problem in the olden days, right? So one famous mathematician, his name is Euler, he figured it out,
oh,
right? So the way he figured it out is, turning this into a graph, right? As we've shown in this illustration here. So if you look at this landmass of A as a node, right, in this graph, because how big is the land doesn't really matter, right? For this particular question, you're as long as you cross the bridge into A, you're in that spot, right? And so this map of the city is equivalent to this graph in solving this problem, right? And the bridges basically become the edges in the graph, right? And so you have these vertices A, B, C, and D, and then the edges are the bridges, and these are how they're connected, right? And then here again, we introduce a concept called degree, right? The degree is live transcript, okay. The degree of a node, for example, A, is basically how many edges that are connected to it, right?
3.
So A has 3, right? And D has 3. B also has 3.
Yeah.
C has 5. Right? So what are these numbers? 3 and 5.
3 3s and 5.
These are odd numbers, right? These are odd numbers. And so Euler figured out if you want to be able to traverse the graph, they should have a shade on that window there. You can only have less than 2. Well, not less than 2. Either no vertices, no, none, right? Vertices, or 2 vertices with odd degrees, like 3 or 5 or 1 or not 1, but 3, 5, 7, those kind of degrees, right? So in this graph, we have A, B, C, D nodes, right? And A, B, D each has 3 degrees, right? 3 connections, and D has 5. C has 5. So you got 4 nodes that are odd, that have odd degrees, right? And so that makes this not traversable.
So you can't do it.
You cannot do it, right? And right. So, and also this concept of Euler path with the mathematician's name, right, named after him, and that is a path that you start at a point and then you walk through the path that you actually go through all the edges in that graph once. That's called a Euler path. Right? So that means the graph has to be traversable in that case. All right. That's the problem of traversability. So, any questions? Right, so we have these concepts, right? Vertices, edges, remember what these are, right? And path, right? Path is basically, a path is for you to be able to go from one node to another, whichever way, right? And traversability, right? And then salesperson's problem, where you can find the shortest path that go through all the, all the nodes. Right? Let's go through all the nodes without, having to go back and forth, right? And traversability is to be able to go through all the edges, right? These are two kinds of problems that come with graphs. And then you have connected graphs and disconnected graphs.
But complete graphs.
And complete graphs, correct. And with complete graphs, you basically have a direct connection from one node to every single other node, right, in the graph. It's a complete graph. And with that, you have, right, the number of edges equals to the number of diagonals plus the number of nodes, right? So that's it. All right, let's take a break for 10.
We're gonna do like sample questions and content questions.
Yep. All right, everyone, we are getting started again. So in the elementary level graph theory, we're talking about a few problems and concepts and definitions, right? And in the junior level, all these will not show up in your contest, right? But this is what's going to happen in that at that level. We have directed graphs, right? Directed graphs meaning that on the connections there are directions, right? So for example, here in the A and B between A and B nodes, right? You can travel from A to B, right? But you cannot go from B to A. That's what that direction means. And then in here, the most interesting stuff, or I guess the mathematical stuff, is this matrix called adjacency matrix. An adjacency matrix is basically something like this, right? You have a matrix, and however many nodes are in this graph, you list them at the head of each row and also the head of each column, right? And then if there is a connection, say from A to B, you put a 1 down there, right? A to B, AB. And then you have from A to D, you put 1 down there, right? And then you got all the connections down, then you fill it up with zeros. That's a matrix, right?
But then why is there a 2 at the 1 at the bottom of the path?
These,
No.
this is what we're going to get to, right?
Okay.
Remember we talked about the length of path, right? So this means you have, wherever you have a 1, you have a path of length 1 from that node to the other node, right? So from A to B, you have one, A to B, sorry, A to B, you have one. And then from A to D, you have one, right? And then this only says that, right? This only says you have a length of one path from one node to another. And then what if we want to find out paths of length 2? What do is you do this multiplication of these matrix of this matrix. So you do m times m. You guys haven't learned matrix yet, right?
Yeah, we have.
Right. So so when you do that multiplication, you get this m to the power of 2 here, right? And this is what that means. This is the result of m times m matrix. Okay, and the 2 here means that you have two paths from A to C of length 2. Okay, if we look at this graph, right, we can find out that we can go from A to B to C, right?
And then A.
And then A to D to C, that's 2. Right? And actually this trick or this formula works on all other lengths, right? So if you want to find out if there's a path of length 3 from A to some other node, you can do a multiplication again, right? So m to the power of 2 times m again, and you get a matrix of this size, and then you have numbers in there, and then that'll tell you whether or not you have paths of length 2 in there. Actually, there's in this one. So in this one, this is the original matrix, right? M, and then m to the power of 2 is this. And in this, actually, you do have edges that goes from the node to itself. Okay, so there. That counts as a path of length 1, right? And then m to the power of 4 means how many paths you can have from this is from A to A, right? So you can go from A to A to A to A, however many times you want to. So that path is always there. And then you can also go from A to C, right? And then C back to A. So those type of that basically gives you a way to figure out if you have path to another node. And this is actually the an algorithm basically for figuring out what is the shortest path on a network, right? To go from here to there, right? Because again, as was shown in this internet case, right? In this kind of case, you literally have no way to eyeball, right? What is the shortest path from one point to another? There's just no way to do that. But you can use computers to do the matrix and figure out, right, if a path exists or not, or if you have multiple paths to get there, which one is the shortest path? So those are important things. When you're running a network, to be able to figure out. So that's what's happening at that level. Okay, so now we got a couple of problems we can try here. So as you can see, okay, this is a contest sheet for this season, right? 2020 to 2021. So the first problem is first letter of each person's name, right? With A, B, C, D, E, basically. So it tells you who is friend with whom, right? And now you draw a graph to present that relationship, all that relationships, right? So, let's see. Let's see what we can do here. I'll have to stop sharing. So A, B, C, D, E, right? So if I stop sharing and I use my video,
Go to view.
and
Go-
pin this thing, right? Yeah, and also use, no, that doesn't work. Speaker view. Okay, so and just use this half. Does that work? Actually, to make this a little, no? Oh, you have to make it bigger, actually. Okay,
You
and
can't see the full question though.
okay, now we can see the questions, right? So basically we have 5 friends, right? 5 people, A, B, C, D, E, right? So let's say if we have A, B, C, D, and E.
Wait,
Right.
there's Fran, no, there's Fran. On
Oh.
here.
Okay,
There's 6.
sorry, 6 then.
I got me confused.
Yep, okay, thank you. So it says Anne is friend with Deb, right? So there's an edge there, and also with Eve, right? And Eve is friend with Anne and Carol. So A and E is already there, right? So undirected graph, right? So we don't need to do much else. And so where are we? Eve is friend with Anne and Carol, and Deb is friend with Carol and friend, right? Carol and
That is friend with Fran.
friend. And then Fran is friend with Anne and Carol.
Big
It's not with friend with Deb.
Uh,
That doesn't make
Carol
sense.
is friends with Beth and Anne.
No, what I'm saying is friend, right? It says friend. Deb is friend with friend, but Fran is not friend with Deb. That's wrong. Okay, because we're actually drawing. It's telling us to draw an undirected graph, right?
Carol is.
That means this relationship have to go both ways. But anyway, and then Carol is friend with Beth and Anne. So
Okay. that's
Beth
Fran. And
and
Beth is friends with
Anne.
Eve and Deb.
Beth is friend with Eve and Deb.
Oh my God, what did I make?
Right, so this is like a convoluted.
Oh my
Graph.
God, no,
But-
this is really weird.
but I guess it works, right?
Alright, wait, it says which person has the most friends? I should have drawn a bigger path. Well, okay, so let's see. One, two,
Well,
we can count this. We can count this.
It's definitely Carl.
Is that Carl? 1, 2, 3, 4. Carl has 4 relationships.
Carl has
No,
so
five.
does Anne, right?
Wait, it says here that it's 4.
But I thought Carl has a 5.
Um, oh my
So A
God.
and C and D, right? A, C and D. I mean, if the relationship goes both ways, right? And because we're talking about undirected graph, so
Wait, Carl only has 4?
Well, on that one.
Yeah.
Eve is friends with Anne. Eve is friends with.
Anne also has 4. Deb also has 4.
Deb is friends with Carl. Carl and.
So what are the,
Hold on,
I
I'm
guess.
rewriting mine. Fran is friends with Anne.
I don't know.
Wait,
So you have to choose one.
I don't know, but it's like. And then Carol is friends with Beth and Anne.
Wait, how did I count 5 for Carl?
I have no
You did?
What? How? What? Can some of the remote people help us? That's
Definitely.
kind
So what are your answers? Or what,
Okay, so
here's my chat window.
okay, we should start with this one. For me, Anne has 4 paths. F. Fran has 3.
I literally remembered all the
E has
names.
oh my god. E has 3. Deb has 4. Carl 2. Wait, no, Carl does have 5.
Is that 8? Okay.
B 1.
Did Carol?
Beth has
Carl.
3. Okay, so Carl has the most.
Wait, so that means they don't need to draw an graph. I'm literally drawing a new graph to prove that. Carl.
Yeah, Carl has the most.
I'm just gonna say all of them are friends with each other. This is almost what it would be like if all of them are friends.
God.
With friends and
Oh, I missed one, I guess, or I drew one wrong. No,
Carl has no for us.
I missed
Carl-
one here, right?
Carl has the most.
You're right. I think Carol has 5.
this is
Yeah,
what it
Carl.
would look like if all of them were friends with each other.
Yeah,
Lunch.
well, Anne is not friend with Deb
Okay,
or
so
Beth.
First
That's
one
why.
is equal to
guess.
C. And then, so we go on to the next
Right.
questions, right?
Yep. Okay, the next question is,
For the given graph, how many more edges are needed for this graph to be in a complete? graph?
complete graph. Okay,
E, Q, T,
let's try to
F.
figure that out.
So it's like a pentagon.
Yep.
It's an upside down pentagon. Okay, so. This is gonna be a hard one.
I already miscounted.
All right, so So this is, okay, so if it was complete, it would have one. No, it would have 10 sides, no, 10 edges if it were complete.
Right.
So 1, 2, 3, 4, 5, 6. Wait, hold on. Wait, 1, 2, 3, 4, 5, 6, 7. Okay, so that one has 7 edges. So if we,
Three.
no, yeah, it would be 3. So it would be C.
Yeah, okay.
2 is also C. Okay.
3 more.
I think I see a pattern. 3 is C, 4 is
Oh
C,
my-
5 is C. My God.
No, no, you said I see a pattern. Get it, get it, get it. I see. Corny joke.
Okay,
I
In,
read this
Three.
as C.
in creating a transportation network among the cities of Austin, Boston, Concord, Denver, and Frankfurt that uses the first letter of each city's name, how many different routes or simple paths are there from Austin to Denver?
That's gonna be a hard problem.
No, simple paths, what, different routes. Okay, so 1, 2, no, 1, of course, it would start with 1. Okay, so there's 1 path. So then there's 2, and then 3, 4,
1,
5. I've counted 5 so far.
wait, simple paths?
No, just different routes.
5. Imagine if it was A to B to F to D.
I think it's B for some reason. Maybe I'm missing something, but I think it's B. Wait, hold on.
What about A to F to B to C to D?
I already did that. Okay. Wait, 1, 2, 3, 4, 5. Okay, that's 5 so far. Yeah, I think it's 5.
Wait,
No, I'm pretty sure it's 5.
are you allowed to like repeat paths?
that's the question.
Because I would like
What I think is,
B, C, A, D.
what I think is that it's asking routes from A to B, right?
Yeah,
From A to B, from
Austin
Austin
to
to
Denver.
Denver. So A to B, you have 1, A to B, right?
Mhm.
And then for other routes would be from A to any other node and then get to B.
I'm pretty sure it's, you can only go to each vertice once. So it's like a
True,
wait,
But-
what was the thing again?
but what that means is that you can go from here to here to here.
Mhm.
But then you can also go from here over here,
Yeah, that
and then
works.
over,
Yeah,
right? So anywhere you have one extra path, you can basically, you have an extra route, right? From A to F to B to C
Yeah, yeah,
to
yeah,
D.
yeah.
And you can go from A to B to F to D.
Oh wait, no, that's 6. That's 6 then.
Exactly.
Okay, so it's C again.
C.
It's C again.
C, I
Oh
told
my
you.
god, why are all these answers C right now?
Because it's ACSL. And leave out the A.
Right, I think a simple path means that you cannot, basically, you cannot go back to A and then.
Yeah, yeah, yeah.
Right,
Wait,
that's what
if it's
it
actually
means.
following ACSL, then that means the test before this, all of them were A.
No
And then this one's gonna be
way.
C, and then the
No.
next
Okay.
one's gonna be E, and then the next one's also gonna be E, because you can't show those letters. So you show the highest.
Well,
letter.
that's not easy. Okay, so the first 3 questions were all C. Can we confirm from the remote side?
Oh, we can try.
Can we confirm okay. Is there like more questions or is that all? 3?
There are more questions.
Oh,
Well, let's
Oh,
see.
fine.
Where is it? Which one is that? I think C4. I think it's this one.
2020 LM dot sol. Oh.
Well, actually, it's not C. It's 7. Okay, let's see.
D. It's D. Wait,
Let's
the
see.
7 simple. No, wait. Wait. Did we miss something? A B A C D A F D. Wait.
So we obviously missed something. Let's see what we missed.
Wait, hold on. Wait, A D
Something.
A C D A F D A B
Oh, come on.
C D A B C D. Wait, really?
Wait,
Wait,
I'm
can we
gonna,
go
I'm
back
gonna
to that?
record the other answers. So it's
Wait, can we go back to the past?
BA.
Wait, yeah, we did A B C D, but then there's
Bah.
wait, there's A B F D. Okay, we did that. A F B C D. Okay, we did that. A C B F D.
Isn't ACD like?
I think we missed A C B F D, or maybe it was A F B C D. A C
Right.
B F D. Yeah, okay, and then there's A F B C D.
Oh, ACB.
Okay, so then it is D. So not all the answers were C. Wow.
So we had what? We had this 4, right? These 4, and then go out
Yeah.
here. 5.
Wait, can the people see it? I don't think they
And-
can see it.
6, and 7. Okay.
The Zoom
Yeah.
like annotation
Wait, you
tool
can
is
share.
just too hard to use it.
So
I wish we had a mouse with 10 speed. I think you have to share this.
which one did we miss?
No, I think you have to share your screen to show the question. I think we missed like one of these.
Oh,
two.
yeah. Sorry, I gotta share my screen. You're right.
Imagine if it's A, B, C, D.
So sharing my screen here.
You guys see it?
Connie.
Yeah.
Okay. All right, and then. Wait, I think there's more. Go down.
What's going on
What?
here? Okay, that is the,
Keyboard.
I see.
okay, AD, ACD,
AFD.
AFD, ABCD.
ABFD. Okay, you found ABFD, and then I think we missed either AFBCD or ACBFD. I think we missed.
ACBFD is what I missed.
Yeah, I think that's what we missed. Okay, next question.
Oh, yeah, ACBFD, I guess that's
ACBFD.
the one. Okay,
Yeah,
next question
don't go
is,
down on the answer key because we want to solve it.
But what
Okay.
if I already saw the?
don't tell.
Okay.
So number 4 graph theory in the undirected graph,
shown below that.
Al,
represents-
Ben, Cy, Dave, and Eli.
No, Al, Ben, Size, Dave's, and Ellie's house using the first letter of each name. Okay. How many cycles are there? Oh, so we have to figure out how many cycles are there. Yeah, that no.
1 cycle.
One, 2. This is gonna be hard. Okay. 1, 2, 3, 4, 4,
Well,
5. Okay, it's past 5, so I think there has to be like some sort of strategy.
What?
Feels like time.
okay, did anybody type anything in the chat window?
Where we
See,
go down to
I
this
should be able to find it.
1. 2, 3, 4,
Where's the chat window on here? Oh,
1, 5, 2,
1,
3,
2, 3. Oh, it's on.
oh, it's time.
We can finish
No.
these 2 questions next time.
Okay. All right. We'll do it next time.
Yeah, I feel like there has to be like some sort of strategy. Some sort of strategy to make this easier.
Yeah, I suppose you can,
Wait, maybe instead of like trying to find all the paths, just try each letter.
Write the letter?
you can, try them in order. right?
Yeah,
So
yeah, yeah, yeah.
A, B, C, D, E, A, B, C, E,
ABCD.
A, B, C, E, D, A.
Like what I mean
things
is
like
like
that.
try from E and if we know 12 paths, go to D and then C, D, D.
Yeah.
Let's try. All right, thank you. Thanks, everyone.
Thank you. Bye.
Have a nice weekend.
You too. Thank you. Bye.
นี่ก็ใช่ไหม
Bye-bye.
ที่บ้านไม่ค่อย
Weekend.
Oh, yeah.